Well, hey there, folks. Quick lesson. Hopefully I'll make it a quick lesson. The title of this one is Naming Ionic and Covalent Compounds. And we've got some multivalent stuff, some polyatomics to talk about, so let's get right to it. All right. So the very first thing you have to consider when you name something new that's formed, when two chemicals come together, let's say if it's iron or oxygen, or if we have oxygen and fluorine coming together. Now, I know that can sound a little bit strange, but it really depends. Are we talking, step one, about ionic? Now, that would be a metal and a nonmetal, something from the left side of the periodic table and something from the right side of the periodic table. Okay, that would be ionic. If it's covalent, that's when there's an electron sharing arrangement. That would be when two things from the right side of the periodic table, two non-metals, are sharing. Okay, so first, it's that game of give and take, right, with ionic compounds, metals and nonmetals. There's a naming system for that. Whereas with covalence, we're only talking about nonmetals, right? Everything from the right side of the periodic table. So first thing you have to recognize is I say, look, is there a metal involved in there at all? Because if you see a metal, bam, you know it's ionic. And you can go straight to those rules. Okay, so it's pretty much a yes-no decision. Now, when you look in the periodic table, you might have noticed this. And I've referred to this before, but this is called an oxidation state. I know, big word. And what it really means is, what is the ionic charge of an element when it becomes an ion? Potassium, sodium, lithium, they're all +1. If you look in the middle of the periodic table, you'll notice that some things like iron and nickel and manganese, they can have multiple oxidation states. The way I explain it is they're willing to make different deals to satisfy their electron and orbital needs. Here's an example of one of those multivalent ones. And it really matters because there are three different kinds here. Actually, with manganese, there's more than this. We're just showing you three. There are three possible ionic states it's willing to go to make a deal in order to become quite stable. So, because there are these different forms, you have to say which kind of manganese has shown up to the dance. Iron does the same thing. We've got iron 2 and we've got iron 3. In this case, we've got manganese 2, we've got manganese 3, we've got manganese 4. So you have to be specific. Okay, and this comes up with the metals, okay, with the ionic bonds. So, simple ionic naming. Take something like magnesium oxide. Now, how did I know to say that? Like straight up. I said magnesium oxide. So the first thing I did is I named the metal. And you don't do anything strange with the name. The first element just gets called out for what it is. You just say, hey, magnesium, how you doing? Okay? Magnesium. And for the second part of this compound, ionic compound, you kind of keep the root name, oxygen. So you're like, okay, oxy, and then the rest you're going to put in is an IDE. Now notice we're only talking about one element there. Okay, we're not talking about a polyatomic chunk, but because it's just oxygen, we say oxide. Okay, we don't want to say oxide, that would sound kind of odd. So that IDE thing is a big deal. So its name is magnesium oxide. Now I didn't have to say which kind of magnesium because magnesium only has one oxidation state, one charged ionic self. Magnesium oxide. Okay, so here come a couple more players. When you look on your periodic table, I'm going to just jump because there we go. You'll see periodic tables like this. And in the case of lithium, if you look over in group 1, right here, the second row, third item, lithium, it's got +1, right? And if you look at fluorine, which is atomic number 9, it's -1. They only have one oxidation number, right? +1, -1 relatively. So you look at a periodic table like that, and you say, okay, first one is lithium. And the next one, you don't want to say fluorine right? It's got to be slick. So you say fluor, F-L-U-O, I will spell that wrong, I-D-E, lithium fluoride. There's that "ide." Notice it's only two kinds of elements in this dance. Now, if you magnesium, previously we saw that it only has one oxidation state, and I'll give you a hint, iodine only has one as well. Take a look at iodine. It's in the halogens, the 17th group, and they're all -1. So you say magnesium. And since there's only one kind, you can just go straight to the iodide. Boom, done. Scandium. You look at scandium. Okay, so SC. You start searching around the periodic table, and you look 4th row, 3rd column, 21st element, bam, scandium. Oh, good, right? Titanium beside it has different oxidation states, but thank goodness scandium is +3. Okay, that breaks things down for us. Scandium, there's only one kind, so we don't have to say which one. And then you just say, well, you can't say oxygen, so you say oxide. Boom, you're happy? Okay, so when it's two elements, it'll usually be the first element and then the next element, ide. Sometimes you have to slip, if there's different forms, different oxidation states, you have to say which one it would be. And I'm just drawing an arrow as to where that would be put. But in this case, they all have just one oxidation state. So you don't have to say what kind of scandium it is because there's only one kind. Okay. If it's covalent, right, you won't be seeing a metal. And remember, most often we treat hydrogen as if it's non-metal. Okay, in more advanced chemistry, you can consider hydrogen in a different context. But we'll take a look at this one. So we've got H2O, right? Now, we know it's water. That's just the common name. Okay, but that's not chemistry. No, you have to learn rules. Drive yourself crazy. That's okay. That's why we're here. When you look at the first element, you would say, well, that's hydrogen. I'm going to put some space in between the names, okay? And the second element is oxygen. So I'm going to write down oxide. I got to give away a little bit of it. So you'll see that ide is still there. But did you notice that there's two hydrogens there? When it's covalent, you have to say, if there's two, if the subscript is 2, you actually have to say di. Now, it's kind of interesting. If there's a subscript 1 there, you don't have to say mono for the first one. But if there's a 2, you have to say it. And I haven't left myself space, so I'm going to say dihydrogen monoxide. There's a famous website, if you want to go check it out. It's called Dihydrogen Monoxide Can Kill You. And it's all the things that water can do and that can sort of end our existence. We can drown in it. If you drink too much, it's toxic. Yes, it goes on and on and on. Dihydrogen monoxide. It's, if you want a bit of a laugh, it's a funny website. So, dihydrogen monoxide. Below, sorry for the little mess there, but below what you're seeing is this is N2O4. Now, that is a proper electron sharing arrangement. We don't have to get into that. But if you have the molecular compound, remember only, when I say molecular compound, I'm talking about covalent compounds. Because there's a 2 there, you have to outright say it, dinitrogen. So the root word, right, is nitrogen. So you go with that. The next word, you say the oxide part. Now that reminds me of what we were saying when we were naming ionic compounds. But you have to say the number in front of it, because that's a way of indicating the subscripts. Please don't do that if we're talking about an ionic compound. It's only for the covalents. Only for the covalents. All right. So let's say we have a binary. Now this is a fancy. It just means 2-part, right? Binary, 2 things, right? 2 elements combining. In this case, we've got silicon and we've got phosphorus. So what in the world do you say? You say, sort of look at it and you say, well, try silicon. And then you're like, well, what the heck do I, Tri is a pretty easy one. These are those sort of prefixes you've seen before, right? You've got mono, di, tri, tetra, penta, hexa, hepta, octa, nano, deca. Yeah, I know, it sounds like you're learning the metric system again. It's a lot like that. So I saw the 3 and I wrote down tri, silicon, and then I know the next element's going to be phosphorus, but because there's 6 of these lovelies here, I have to say hexa, and then I have to say phosphide. Whew, that's a mouthful. Trisilicon, hepta, phosphide. It's covalent, folks, so I'm obeying the rules. It's a covalent binary molecule, which means it's covalent, 2 nonmetals. There's just 2 kinds of elements playing out here, okay? So the rule is, why did I not write phosphorus before silicon? Well, who's closer to the dividing line between the metals and the nonmetals? Find that dividing line, and whoever's closer gets named first, because they're technically the most metallic, even though it's not a metal. It's a thing. You add "ide" to the second part of the name, right? So you write them down, and then you got to remember to put in the prefix. So here is a nice little table. You can look these up. They're pretty straightforward tables. Boom. We had tri and hexa to deal with in the name of this. So trisilicon hexaphosphide. Not bad. True story. Now, you should stop right now, and because we're doing covalent naming, you should, press pause on the video right now and see if you can name these yourself, right? I'm going to give you a second, so pause. I'm assuming that you took a lot more than a second there, okay? Coming back, you might have wanted to say, did you try to say monophosphorus? Because you never say, if this number here is a 1, you don't have to say mono. You never have to. It's only when it's 2 or more. So we don't say monophosphorus pentafluoride, we just say phosphorus pentafluoride. Over here, there's that tetra, right? Phosphorus is more to the left, tetraphosphorus, deca oxide. Now, you're probably going to say, whoa, 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 hypocritical, hypocritical. Over here, some of you might have tried to say dinitrogen, right? You're thinking, why dinitrogen oxide? And you're saying to yourself, oh, wait a minute. You said if there's a subscript that's a number 1, you don't have to say it. Hold on, here's the catch. If the subscript is for the first element, you don't say it. But, lovely chemical naming conventions, if the subscript is 1 for the second element, you gotta say it. So, yep, mono is said for the second thing in a binary covalent compound. Whew, say that 5 times fast. Yep, so there's your dinitrogen, and you had to say the mono. You heard it here first. Well, maybe not, but we'll try to take credit, won't we? Boom. Okay, so multivalent. Notice that we have a metal. Now, when multivalency comes up, yep, we're pretty much talking about metals. So we're kind of bouncing around here, but we're going back to some ionic naming. Why? Because we're talking about multivalency here, right? Which I mentioned a little bit before. Plus, there's polyatomics to consider. So, whoa, let's get down to this. So when you look at manganese, you're like, okay, which manganese am I talking about here? Because the last time I checked, going out to the old periodic table, this one, right? Manganese is element 25. That's in column 7, right at the top. And you'll see that there's actually 1, 2, 3, 4, 5 oxidation states listed here. Okay, so manganese is willing to make different electron deals. Let's keep it that simple, okay? Oxidation states. Okay, so which manganese are we talking about here? Well, if I look at oxygen there, I know that oxygen is 2 minus. Oops. It's getting ahead of me. So if oxygen is 2 minus, and I'll just write this a little bit to the side here. Oxygen, 2 minus, and we have 2 of them. Well, that's good for 4 minus. Which kind of manganese is going to counteract a 4 minus? Well, if there's just one of those manganeses there, right? If there's just one, and understood one, and this is the ionic compound, well, that's if it's just going to be manganese on its own, that's got to be 4 plus manganese. Then you have 4 plus, 4 minus, and these come out to neutral, right? So those are the proportions. And when I learned this trick about oxidation states, I was able to figure out the formulas for ionic compounds. You can always figure out the formulas for ionic compounds if you know what the charges are, right? Helps you along. So we say manganese yada oxide, except which manganese are we talking about? Well, that manganese is going to have to be manganese of the 4 plus variety. So you use the old Roman numerals, folks. Gotta love them. And you have to put in brackets. So we're talking about manganese 4 oxide. You have to do something. So that little interruption there is a thing. So we figure out the charge, make sure it's all balanced out, and we've got manganese 4 oxide. True story. Now, there's different kinds of iron. Fe2O3, well, that's rust, known by any other name. When I look at Fe2O3, I'm like, okay, multivalent naming, which iron is this? You notice we're always talking about which metal? That's right, because it's always the metals that are doing these multiple oxidation states. So, off to the side, if we've got O2 minus, O2 minus, O2 minus, that's solid for 6, a net negative charge of 6 minus. Okay, so if we're talking about iron here, which iron is it? Because I said there's Fe and there's Fe. Okay, I'm looking at the number 6 and I'm thinking, I've got to get 6 plus. How do I get 6 plus? Well, if each of these are the same, what's half of 6? There's 2 of these guys. 3 plus, 3 plus. Oh, okay, so we're talking about the 3 plus oxidation state of iron. Trip to the periodic table. I don't want to make you dizzy. But we'll go to iron, atomic number 26, and you'll see that there's a +2 and a +3 version of iron. So they're different. So you say, well, this has got to be iron 3 oxide. And anyways, here comes the table with the rest of the details, right? You figure out that here you've got a 6 minus charge, as we kind of did above, and the only way we can get to 6 plus is if we have 2 atoms to get us to 6 plus. We need 2 irons, and we have 3 oxygens. +6, -6, this puppy's balanced. It's a good thing. Iron 3 oxide. Now, you notice I'm a little older, so I did my 3 like this. That's okay. You don't have to. It's fine. Okay, practice problems. This is where you hit pause. And you go out to your periodic table, kind of like the one that I had in the Firefox browser there, and you say, holy smokes, if I have to take let's say I have a case here where I have the formula, I have to take the formula and get the name. Well, how's school going to work? It's always going to work 2 ways. Okay, here's the name, give me the formula. So pause the video, take a couple of these out for a spin, pause now, and then come back. Okay, welcome back. Now I'm hoping you paused the video there. Thallium 1 nitride. Nitride's kind of an interesting one. Nitride itself, you're wondering, okay, what's the charge of nitride, right? And if you go to your periodic table and you look at nitrogen, right, you'll see that there's some interesting oxidation states, -3, and then you see some positives. Only reason you see some positives there, and I largely say discount those, because we're talking about an ionic compound. As soon as I saw thallium, I know that it's a metal. Go with the negative oxidation state. Because nitrogen is so darn close to that metal-nonmetal line, under certain conditions, it can act, because it's touching it, it can act like a metal and a non-metal. It's very close, right? There's some nuance to this. But when we say thallium nitride, and I see that name, as soon as I see thallium, I know it's a metal, right? So thallium, You could always look up thallium. It can be a little bit hard to find, right? Put on your glasses, where's thallium? But here's a trick. If you're looking at thallium, based on nitride, nitrogen, if it's acting negatively, well, it's got to be the -3 charge. Okay, so if this is -3, and we have thallium, and they're identifying it, this must be, when you find it on the periodic table, you'll see it's 3+. So you've got your thallium nitride, and thallium's one that I have to find. Good old thallium. Where are you? Thallium, thallium, thallium. I don't see it. So let's call up thallium. Boom. All right. So thallium, Ti, here we go. It's number 81. Let's go back to our periodic table just so I can find it. All right, there it is. So element 81, and it has two oxidation states, +1, +3. Well, if there's only one thallium showing up, it's got to be that +3 one. So thallium nitride, right? Pretty cool. If we look at palladium 2 phosphide, what's the charge of phosphorus? Okay, so when I see palladium's a nonmetal, and they're basically saying right out front, it's 2+. All right, palladium phosphide. Where's phosphorus? Phosphorus has a -3. Again, ignore the positives because those are exceptions rather than rules at this point, right? So if we look at phosphide, it's -3. Okay, so palladium, right? We're going to need PD. We're going to need a 2+, a 2+, and a 2+. The lowest common multiple of 2 and 3 is 6. So if we're looking at palladium 2, right, we're going to need 3 of those, and then phosphorus is 3-. We're going to need 2 of those, right? So PD. And you could do that. Remember that trick where you cross like this, right? Where you do PD 3 and then P2. That trick, all it really is the lowest common multiple trick. You just take the charge and you write it as the subscript, and you just cross them over for the elements. It's kind of cool. Okay, lead, this tells you you're +4, and oxygen, we'll speed this along now, is -2. Okay, so that's PB, and you'll notice I'm not writing Roman numerals. You only write Roman numerals when you're talking about the names. PbO, we're going to need 2 of these oxides, right, to balance out PbO2. Now, along comes lead 2, a different oxidation state of lead. We know that this is +2 and this is -2. So you notice these formulas, one is PbO2 and one is PbO. Okay, different recipe, different proportions. In the ones below, just to speed things along, I won't do all of them, but you've got molybdenum. You're like, molybdenum, right? And there's a trick. If you want to figure out what these charges are, right, what must molybdenum's charge be? Well, oxygen is 2-, 2-, 2-. So this has to be the molybdenum 3+ version, because that's the only way it's going to balance out. So I hope I got the spelling right. I'm not checking. Molybdenum 3 oxide. Not bad, not bad, not bad. Down below, I'm not going to hit all of these, but there's 2 different irons at the bottom that just have to be addressed. Okay, I'll skip 2 and I'll do 3 and 4. We know that this is the oxygen is always 2-. The only way this iron is going to work is there must be this, if it's going to be just one, has to be a 4+ state of iron. Wow, there's a lot of types of iron. So this would be, now always check your formulas, because if it turns out that there's an error in your formula, or let's say iron 4+ didn't exist, you should always check back in the periodic table. Always double check. You got to have your formulas right. But this would be iron 4, written like that, and then oxide. Over here, if this is 2-, then this is the 2+ version of iron. So then that's iron 2. And then you say the oxide, right? And these are what we call binary. These are binary compounds, right? 2-element compounds. It's not going to stay that way. Right now, we're looking at the oxidation states. We're keeping it pretty simple. Just two ions coming together. What the heck are the names going to be, okay? But we know there's some funky ions out there, aren't there? Right? I'm just going to go past this quick now that you've had a chance to see it. There's these things called polyatomics. And if you look at them, you'd be like, wait a minute. It looks like these are covalent, and they're not sharing quite properly, and they kind of have charge imbalances. Yep. And if they come together and they act in a way where they're positively charged or negatively charged, folks, if you have a negatively charged item, that's acting like an anion. These are all, well, actually, these two are acting like anions. And over here, because of this positive charge, even though nitrogen and 4 hydrogens are hanging out and sharing, it's positively charged. Its overall charge is just one more in the positive tank than it should be. This is acting like a cation. Now, here's a way to think about cations and anions. In this case, even though they're polyatomic chunks, if you're negative overall, right, you're going to be an anion. And if you're positive overall, you're acting like a cation. True. Okay, so we're looking at polyatomic or many ions. And these can come together, even though they're covalent, they can act like they're ionic. I know, it blows your mind, but pay attention to the positive and negative charges. That kind of simplifies things. So in a table of common ions, you'll see them listed, and I showed this in a previous lesson. We've got ammonium, right? Cations. I positively like cats, that's how I remember it. And then our anions. But these are polyatomic deuters. So, once you get really good, you'll start to memorize these. It's kind of interesting, I know, but it's what we do. Polyatomic ions. So if we're going to look at, let's say we look at a polyatomic here. We say, well, what the devil is that? If you look on a list of polyatomic ions, PO4 is known as phosphate. Okay, you don't change its name. If it's a polyatomic ion, it's a cluster, it's a group, you have to call it by exactly what it's called, right? So this contains 3 magnesium ions, right? And you have to consider the polyatomic as a group, and that's really handy to do. You notice that the polyatomic has these brackets around it to keep it together, and then you say, oh, there's 2 of those PO4s. So we've got 2 of those phosphate anions, okay? Now, if you think about what that means, let's do a little counting here. PO4, right? And that's a 3 minus charge, and a PO4, and that's 3 minus charge. When you think about, well, how many, like, if we're talking about 2 of these coming together with 3 magnesiums, we have to account for how many atoms are there. Well, there's 2 phosphorus atoms, if you count them all together, and it turns out that there are 8 oxygen atoms. So just look at the subscript, and this is like, wow, there's 8. Okay. If we look at sodium carbonate, right, CO3, known as carbonate, is a 2 minus ion. Okay? And I've done this so long, I just know as soon as I see CO3, it's carbonate, right? Okay, so what we've got is, subscript tells me there's 2 sodium ions, and they're, okay, I'm going to do this, but no, you would never do this. There's just 1 carbonate. You don't have to put the brackets around if there's just 1, right? So you say there's 1 carbonate overall. Now 1 carbonate has 1 carbon and 3 oxygen atoms. Bada bing, done. Oh, the infamous practice problems. Okay. This is where you take things out for a spin. But what you want to do is, and I'll just give you a hint, potassium, go look at a periodic table and figure out what its cation is. Right? Calcium is 2+. Ammonium, off of the table of common ions, is NH4+. Lead, this is Pb2+. I'm just kind of moving that along, right? And then you say, well, what the heck is cyanide? Cyanide is when carbon and nitrogen come together as an anion, and they have a -1 charge. Chlorite is a really interesting one. It's C, and I like to do my L's like this, ClO, and the charge of chlorite is -1. And then there's other weird kinds of chloride. There's hypochlorite. Hypochlorite is a little bit more, it's kind of, I was supposed to say ClO2. Sorry, folks. Hypochlorite is a little more star for oxygen. It's not ClO2, it's ClO. Hypo actually means one less. One less than chloride had. What do they mean one less? One less oxygen. It still has an oxidation state of -1. Okay. Acetate. You go look on the list. What the heck is acetate? CH3COO minus. If you write the name of the players over top, you can figure out how you're going to write it later. Right? Because these guys are equal strength, that's just going to be KCN. Like that. Potassium cyanide. Calcium chlorite. Looking at that, I know that I'm going to need a couple of them. Ca, ClO, and this is where you can get messed up. If you don't remember your brackets, you're going to have ClO22, and that's going to look really weird. ClO2 twice. Okay, ammonium acetate, NH4. Now, because acetate is actually considered to be an organic thing, it's interesting. It writes its carbon first, CH3COO. Okay, got it. If there were more than one of those acetates, you'd put brackets around it. Lead, Pb, and to balance it out, we're going to need ClO. We're going to need two of them. Holy smokes, okay, that's done. Your next job is to look below and figure out the names. Okay, so of course it's a good time to pause and come back, because in about 2 seconds I'm going to go over these. Okay, it's been 2 seconds. When I look at this, I know that it's ammonium. That's its name. Got to use a polyatomic name. I'm not allowed to cheat. Now, it's acting as a metal. So I don't say triammonium. I just say ammonium, and then that's nitrogen, and I do the nitride thing, right? The ide applies. It's like there's two things here, you know? It almost looks like it's binary, but it's not, because that's a polyatomic in front. This is lead. But when I look at OH, I know OH is a -1. If there's 4 of them, this had to be the 4+ version of lead, because there's -1, -1, oops, -1, -1, -1. So that's lead, and you got to do the old brackets. Lead 4, and OH is known as hydroxide. Holy moly. Okay, if you look at the couple of these elements, you'll be hunting around. You'll be like, well, what the heck is CrO4? And if you look, most of these tables are alphabetical, and CrO4 is known as chromate. This is sodium chromate. Just call the polyatomic by name. You're not allowed to change its name. Just call it what it is. What do we got? Calcium. And then you've been looking at HS. And in a periodic table, you go to HS, and it's got 2 names. It's got an older name. We'll start with, it's currently known, most scientifically known, it's known as hydrogen sulfide. HS can be called hydrogen sulfide. But because it's had various names, you might hear HS sometimes being called bisulfide. So calcium, hydrogen sulfide, run out of space, or calcium, if you're rocking it old school, bisulfide. Holy smokes. There you go. Both the names are acceptable. It's like people haven't made up their minds, right? All right, so I'm just going to bring those in. So the rules for naming, here comes a flowchart. If it's a metal, or if there's a metal at all, go off with those ionic namings, right? And it might be simple, like NaCl, right? Sodium chloride. It might be a little more complicated. It might be like, maybe it's NH4Cl, right? Ammonium chloride. Oops, that was supposed to be for that. Haha. What if I had a multivalent? We'll just write one here, right? Maybe you have iron 3 oxide, right? If it's covalent, and if we're talking about 2 nonmetals, right? Well, if you've got a nice simple compound, like, for example, what was one of ours? CO, right? That's carbon monoxide. Remember, you have to say the mono. Oop, run out of space. But if you have something that's a little bit more complicated, what I'm saying is you have to remember to use the fancy polyatomic name. You just gotta. Okay? So you're invited now to torture yourself with some of these formulas for these compounds. As soon as I see, I'm going to give you a hint. As soon as you see tri, tetra, di, whatever, whenever you see that naming system and it's showing up with the second thing, it's kind of a straight shooting heads up that you're looking at covalents, electron sharing arrangements. Now, when you take a peek at these, see if you can do them. I'm going to count to 2. Unos, dos. Okay. Hopefully you've done these. If you haven't, I'm going to stop again. And I'm starting again. Nitrogen tribromide. Now, you're thinking that's weird. But do you remember nitrogen and bromine, if they have to come to a sharing arrangement, this is what it would be. Nitrogen tribromide. Okay. Dinitrogen, well, that's kind of easy. Dinitrogen, 2. And tetrasulfide, and 2s4. Oxygen difluoride? Really? That's kind of crazy. Oxygen with a couple of fluorines. That has to be it. Dichlorine. All right. Chlorine, oxygen. I got to put in the 2. Done. Carbon tetraiodide. That's awkward, isn't it? You know, that AI right there. Carbon, iodine, tetra. Diiodide hexachloride. Wow, you're speaking chemistry now. You've got I2, and hexa is 6. So, Cl6. It's not really that hard once you see the prefixes, right? It literally gives it away. All right, so I just beam those in. Holy smokes, name the following compounds. So this is where it gets all jumbled up. Here what you're going to have is you're going to have some covalents, you're going to have some ionics, you're going to be expected to, look at multivalent, like metals that'll do different charges, and you got to nail it, okay? So, again, you're going to hit pause, and again, I'm going to wait. Who knows? Maybe you're just watching and just, whatever, I'm not going to wait. I'll see how these turn out. Well, try a couple in your head, because pause. Here we go. All right, the first culprit, sodium oxide. Didn't quite hit the line properly, did it? Right? Sodium oxide. What's the next one? Well, that's copper, and that's carbonate. CO3 is carbonate. Carbonate has a 2- charge. So I'm sort of thinking this is copper 2, because I'm going to need a 2+ to make that work out. Copper 2 carbonate. Told you. Okay. V for vanadium. Well, if I've got 2 oxygens, I got a 2-, 2- scenario going on, it's probably going to be vanadium 4. Yep, vanadium 4 oxide. All right. I don't see any metals in this guy. So, please don't say mono for nitrogen, because it is, you never say that for the first one. It's just nitrogen dioxide. Okay? Chromium. You're probably, I don't know, has chromium got 2 oxidation numbers and you madly check? Yes, it does. This is chromium 2. Cadmium bromide. There's only one kind of cadmium. We saw that before. SO2, right? Sulfur dioxide. That's that rotten egg smell. Not good. If you smell that, get out of Dodge. Go outside. See 2 nonmetals here. Covalent. So you just say oxygen dichloride. Okay, there's a metal there. Beryllium, you don't know if it's got two oxidation states. You're supposed to check. There's only one, so it's beryllium chloride. We know that iron is one of those metals that's really willing to make a deal. So this is probably iron 2. How do I know? Because chlorine is -1 and another chlorine is -1. Got to be iron 2. Boom, there it is. Now for the coup de grace, the pièce de résistance, what do we got? Covalent, because those are both considered non-metals. So, let's see. Dinitrogen trioxide. Nice. If you got most of these, give yourself a hand on the back. If you find you're getting mixed up between the ionic naming and the covalent naming, go looking for a metal first, right? Go through, hunt down all the ionic ones. Deal with them first. Then go back and look and see if, is the first one listed a non-metal? Is the second one listed a non-metal? Oh, that's that mono tetra or mono di tri tetra thing, right? Okay, so there's a review here that comes up, and I included these on the end of the slideshow. It was just like a little multiple choice thing. You could take this up for a spin, see if you were right? Okay, so what I'm gonna do is I'm gonna include it, but I'm gonna do the pause thing because, you know, that's always fun. So on the count of 2, pause. 1, 2, pause. Okay, we're back, and here are the answers to those first 2 in the review. Now, if you didn't get these answers, go back, double check your stuff, check it out. Here's the next one. Oops. Got a couple of questions here to take up for a spin. Pause. 1, 2. Okay, and we're back. Answers for these? Just follow the little blue arrow, folks. Okay, I hope that kind of helped out. One more. And pause. 1, 2. Alrighty, and we're back again. And here are the answers for these. Okay, I hope this is helping. Just a little chance to take these out for a spin, right? See if you're starting to get this. We'll do one more. Okay, so pause. 1, 2. And we're back. Which are the diatomic elements? It's all those dudes with the 2s, right? And our second one, right there. Choice D. Okay, ladies and gentlemen, that has been a review of naming ionic, covalent, multivalent, polyatomic compounds. Holy, I always say I'm going to try and keep this short, but I never do. Anyways, that's Mr. B, and I hope this lesson's helped you out. You need to take a lot of these examples out for a spin. It's practice. You do it, and it starts to become more and more automatic. Okay. If you have any questions, let me know, and I'm signing off. Ciao, folks.